Alrighty, welcome to chapter 21 of Earth History for Finland University. We will be covering the topic of climate change today. Now, as a fresh reminder for everyone, this topic very much ties into the previous chapters, so make sure you have read up, understand what we talked about prior to this particular conversation in order to get the most out of this particular conversation. As always, please feel free to comment down below any questions or thoughts you may have. I'll get back to them in a timely fashion. And, well, let's begin. Climate change in Earth's history. The Earth's early atmosphere very likely had a rather substantial large greenhouse effect. Given that the sun was thought to be 20 to 30% fainter, and various deep freezes have occurred 5 times at least. These deep freezes being where the ocean, all the land is covered with ice. Most recently, we've talked about already the Pleistocene glaciation deep freeze that went on. Records show many changes have happened over time with respect to the climate of the Earth, and recent records show mean temperature increases from the late 1800s. We have a chart later in this chapter that explains all these different ways of measuring the climate. I think would be very useful to you. But yeah, the Earth's history has undergone massive change over time, will continue to undergo massive change over time, and understanding these mechanisms is very useful. Here we have a very large and somewhat confusing, you could argue, chart comparing temperatures. So the y-axis scales on the far left over here, we have degrees Celsius versus the average temperature, quote unquote, 1960, 1990. So this would be your average global temperature at 0. Then this would be hotter and colder in Celsius, hotter and colder in Fahrenheit, measuring the same thing by 2 different scales. And here we have a graduated time scale representing thousands to millions of years before present. As you can see here, 5, 10, 15, 20,000, 200,000, 400,000, and then here 4, 5, 10, 20, 30 million. So the scale is in no way, shape, or form even, hence these breaks here. Anyways, what this chart shows is the approximate temperature of the Earth at these particular times. The color of the line changes as set up here at the top based on where the information is coming from. So we have, as said here, this blue part from measurements in Antarctica. These red dots here, Berkeley Earth, Land, Ocean measurements, and then back here, various papers and what have you. And then we get down here into very much approximations. Estimates of global surface temperature over the past 500 million years. The upper curve shows the entire record for 500 million years in 4 separate panels, as I said previously. Notice that each panel has separate time scale on the axes, like I told you. Important takeaways from this conversation. 1, things have been really hot in the past, like super hot, right? 2, the chart itself jumps all over the place as it goes. This is the weather climate conversation, but just purely for climate. 3, these, especially when you get farther back here, are of course always approximations, but there's evidence to verify and back these claims. 4, just as with the weather and climate conversation we had earlier, general trends do occur, and those trends can mean something. And 5, this right here is telling. The lower curve for this zoom in here shows global surface temperatures for the past 65 million years, essentially the Mesozoic-Cenozoic boundary, using a constant time scale for the entire curve, million years ago, MA. Shown also are key tectonic and oceanographic events at the bottom, along with the growth of both polar ice sheets. Here you have Indian-Asian collision. This is essentially the formation of the Himalayan mountains. Circumpolar current shown here, the Isthmus of Panama forming, what have you. And up here we have the Antarctic sheet forming in the northern hemisphere, ice sheets forming. And we can see the temperature shown here in degrees Celsius being very warm, but these ice sheets start to build, and these tectonic activities start to happen, causing CO2 forcing in the downward direction, thus reducing the temperature. And here we have hominins, the great apes, us essentially, appearing at the very end of this conversation after the ice sheets have been created, way past the formation of these big events. Remember, this is only going back 60 million years. So we're talking here. We're talking this section. And again, we see a lot of stuff plays into these conversations, right? Finding the correlation between ice sheets, between tectonic activity, between temperature, tells us a lot about what's going on. Again, we have a long-term cooling trend, you can tell, I'm sure, by watching this chart downward. Associated perhaps with a bit, started more or less with the Indian-Asian collision, the Himalayan mountain orogenic event, and then coincide also with building up of ice sheets in Antarctica in the northern hemisphere. All things to very much keep in mind as we move forward. Here, a more recent chart showing average temperature changes in the very, very recent past. Here we have your average temperature from 1981 to 2010, right here. And then we can see a gradual but systematic climb up, as opposed to the climb down that we've been having as a result of ice sheet formation and various tectonic activities. And more or less different from the slow steady of the Holocene that we've seen in the past. So we have, in general, wobbliness, more or less lower in temperature, stay decaying in temperature, or downward forcing would be a more scientific term, and then an upward mobility and upward forcing of temperatures in the very, very recent past 100-some-odd years. The historical records can tell us a lot about what we do. We measure climate change in the past by looking at these records. For example, we have evidence of a little ice age for some 400 years where things were very cool. Landscape paintings, other historical archaeological accounts chronicle changes of the span of human history, right? What was the temperature like in 1500? Well, I can't ask someone. They didn't really write that stuff down in books, but when they did landscape paintings, we can look at that and we can say, in this part of the world, there's cloudiness, there's snow, there's different vegetation, there's different animals, what have you. That's useful. This chart here is kind of what I'm talking about. Notice here, the y-axis is not really an axis, but the x-axis here is the time range of that climate source of information. Instrument records, of course, the most accurate, the best, right? Exactly what the temperature is. And instrument records can be very useful to us, but we didn't start accurately recording temperature until maybe 100-some-odd years ago. So that kind of peters out with the multitude of accuracy that we can get from that information. However, lucky for us, historical records and tree ring dating, that we'll get into this at later slides here, can pick up the lack of information and give us a better clue about what's going on. We can also look at things such as pollen counts in lakes, oxygen isotope ratios in ice ring dating, if you will. Glacial evidence. Glaciers obviously grow in colder weather, right? We talked about that in previous chapters. And that can give us a clue into thousands, tens of thousands, hundreds of thousands, perhaps, if you go to glaciers, of what the climate looked like. But even beyond glaciers, we can talk plankton. We can look at plankton counts and how that varies with colder and warmer weather. And then at some point, once you get into millions, tens of millions of years old, you kind of only have the rocks and the fossils to look back on. Even that can tell you something about the climate at that time. So these sources of information can give us these charts. This is predominantly instrument record, as said there. We don't need to use tree rings because I have a thermometer outside, right? These guys here dig all of this and then lead itself into rocks and fossils. And then these guys here, basically these last four, are all rocks and fossils, and then also get into climate modeling, which we don't discuss in this chapter, but that's also a very powerful tool. So let's expand each of these shapes, blobs. I don't know what to call that style of graph. I'm sorry. Let's expand those a little bit. Tree ring data. How does tree ring data help us? Well, trees grow more when it's warm and wet, and they get lots and lots of nutrients to grow. So if you cut a tree and you look at its rings, you can count the rings. I can tell you when there was times of growth, or when there was times of quick growth, or when there was times of slow growth. And we associate trees growing faster with warmer climate. So these trees can help us understand what the climate was like as the tree grew. Likewise, plant pollen records are able to show these things as well. They're linked to temperature and precipitation. You have more plants when it's wetter, when it's warmer out, so you get more pollen. An example here being some 10,000 years ago, pine trees replaced spruce in Minnesota, indicating warmer temperatures. The type of pollen, the amount of pollen present in these lake bottoms, usually in bogs, was saved in the rock record, can tell us a lot about the environment that was present, and that environment therefore dictates the climate that was at that spot. You don't have palm trees in frigid climate, so if you find evidence of palm trees existing in the environment, that means the environment at that time was conducive to palm trees. This would be the idea here. As said before, you can treat ice rings in a similar vein, more or less, to tree rings, in the sense of heavier and lighter ice coming from the different oxygen counts and the ebb and flow of the temperature where the ice was growing and shrinking, as we talked about with glaciers back in the day. And again, talking with glaciers a couple chapters ago, the tills, tillites, what have you, provide evidence of the climate of the environment, not only how far glaciers have gone, but also, for example, carbon 14 data logs preserved in that till. We have animals preserved in, the woolly mammoths that are frozen in the Arctic regions of, say, Russia and Siberia, and then you can get plant life information out of that and what have you, providing a very direct clue, a very direct image of the climate at the time that these things were initially deposited. Very powerful evidence to say what we're looking at here. Is it an exact measurement? No, it's not a thermometer reading, but it's a good indication of the overall climate instead of the weather. Remember, climate and weather are two different things. Beyond that, we can also look, as said here, at plankton and the isotopes and ocean sediment. The shells, or their hard parts, if you will, can be preserved in marine rocks and muds to give two lines of information. Not only what was alive at the time the climate information was given, but also, again, these oxygen ratios, oxygen isotope ratios, and biogenetic carbonite. We can have a glimpse, we can have a picture, an image, if you will, of the climate at the time at which these planktons, these microscopic organisms, perished and were buried, and that provides us a clue as to what the climate looked like, so we can accurately conduct these charts and see what trends, see what the climate was up to at those particular moments. And lastly, we can get down to the rock and fossil records. Fossils show what lived where and when. If we have things that appear to be conducive to warm environments, such as ferns, well, ferns don't grow in frigid climates, so we have ferns that tells us there was warmth, moisture, what have you, right? And then, of course, certain rocks form in certain environments, which is useful, but kind of a bit harder to comprehend how that could be useful. So it's more so let's look at the fossils and things along those lines to get us our wonderful charts of the climate over time and how it's changed. Cool. I hope that real fast run through of the various tools and processes of ancient climate exploration provides you a hint as to when a scientist talks about these things, they have rather robust backing to their claims. Shift gears a little bit here. Let's talk about the astronomical causes of climate change. Why does the climate change, essentially? A big component of climate change is the sun. The sun outputs a lot of solar radiation. We've talked about in previous chapters, right? And that solar radiation, while always be an output, isn't a constant amount throughout history. The sun has produced about 70% of its energy it produced today when the Earth was formed. The sun has grown in strength, essentially, as it's gone through its cycle. As the sun heated, concentrations of methane in its atmosphere began to decline as a direct result of this. Always maintain surface temperature for liquid water to exist. Like, yes, this is more of a modeling conversation than like we have evidence of it, like, because you can't really have physical evidence of methane burning off, but the pieces connect to allow the Earth to form as it forms. This can correspond with biolide impacts. This is an event about 65 million years ago that blasted dust and rock into the atmosphere. Essentially, the asteroid that hit the Yucatan Peninsula and killed the dinosaurs. It wasn't the impact that actually killed the dinosaurs. It wasn't the comet hitting the Earth that killed dinosaurs all over the world. It was the climate effect as a result of that, because when the comet hit the Yucatan Peninsula, it shot all that dust up in there, right? When we talked volcanoes, we talked the massive ecological impact volcanoes can have just by spitting a bunch of dust and creating very cloudy, very cool environments. As you know, you go outside a cloudy day, it's cooler than going outside on a sunny day. The entire world is covered in cloud. Things cool rapidly. Dinosaurs, we think, were cold-blooded, meaning they didn't have a way to regulate their temperature, giving us the cool temperatures we saw and the resultant death of those animals. Hey, Joseph, if you got a question, feel free to raise your hand or put it in chat. I can get to that. Otherwise, I'm just going to continue the presentation. You know the drill. No big deal. So, we've talked about the climate change. Climate change has a big effect on the Earth, and one of the biggest things that we care about with the Earth as living creatures is the water. Climate change very much affects water, right? If the climate's cold, you get glaciers. Climate's warm, water evaporates faster, what have you. So let's talk about water in all four of Earth's spheres. Water is the most abundant, water vapor is the most abundant greenhouse gas. That's what's up there in the highest amounts. Glaciers and snowfields, as we talked previously, have very high albedos, reflect a lot of sunlight. So the more glaciers you have, the more sun you reflect, the less sun energy is stored on the Earth. The evaporation of water transfers heat into the atmosphere, right? That's what water vapor is. It's boiling up water. And then, of course, the freezing and condensation of that water vapor that's in the atmosphere releases heat as well due to the same processes. The moving water weathers, erodes, and transports material, and ocean currents move heat around, what have you. Water is very crucial to the climate. Understanding the climate allows you to understand the way the hydrosphere works. Understanding the way the hydrosphere works allows you to better dictate the machine that is the climate. Very interconnected, the two are. And this understanding of the hydraulic cycle and how that works leads us into this fun talk about the carbon cycle. Everything in science kind of runs in cycles. That's a good thing because you want stuff to come back to where it started from, otherwise you lose it, right? The rock cycle allows the same material, the same matter of rock to become sandstone, shale, igneous, gneiss, what have you. If clouds didn't rain, we won't get water, and if water didn't evaporate up into the clouds, we won't have clouds, right? Carbon cycle works more or less in the same concept. Carbon is a rather small part of the atmosphere, but it's very large impacts. If you add a carbon atom to a couple oxygen atoms, you get carbon dioxide. Or add some carbon atoms to add a carbon atom to a bunch of hydrogen atoms, you get methane, big greenhouse gas, important concept, right? And of course, carbon's in the biosphere. In fact, carbon is the biosphere. You are carbon, I am carbon, the woodpecker outside is carbon, the dinosaurs millions of years ago were carbon, we're all carbon. And when you die, the carbon in your body is either released as gas, right? Or if you're lucky or unlucky about how you term it, that carbon that is you can actually be preserved as, say, a fossil fuel, such as the coal swamp or oil or what have you. And the vast majority of carbon on the Earth is in this solid form, such as fossil fuels, what have you. We have a lot of carbon in the hydrosphere, a little bit in the biosphere, a little tiny bit in the atmosphere, but a stupid amount of carbon exists in the rock of the Earth itself. How does it exist that way? Well, this image does, I think, a good example of explaining all the different locations where we find carbon. And this is not to say, remember, when we're talking carbon at this point, we're talking the molecular level, the atom of carbon, not necessarily carbon as in I'm carbon. So I just want to get that out real quick. When we have carbon existing in the biosphere, it exists in many different ways. For example, land plants, your forests, your trees, your ferns, your grass, what have you, consist of a very large amount of carbon because they exist as carbon, right? So when they respirate, they release some of that carbon, that CO2, right? Plants breathe in oxygen, exhale CO2, that CO2 goes in the atmosphere. Cool. Eventually that CO2 may dissolve and get dropped in the ocean. Oceans themselves hold quite a bit of carbon in their plankton and what have you, as shown by the surface oceans and the living organisms. The carbon as an atomic level, of course, CO2, what have you, can also fall into the water, creating carbon-rich deep ocean environments. Not only is the carbon from the whales and sharks and coral reefs and what have you, but there is just atomic level, molecular level carbon in the ocean. That carbon can settle down on the ocean floors, creating your shales, your limestones, what have you. This is a vast amount of the carbon in the world is composed of those shales. Those carbonites, we talked about that a lot way back at the beginning of the chapter, the different types of rocks that exist. Your carbonites are a very large proportion. Carbon as an atom is in a lot of chemical equations of rocks for a reason, because carbon is always moving, flowing around. The ocean floors are packed deep with carbon. Of course, we can also leave the ocean floors and come down here and talk about living creatures, cows, pigs, you, me, what have you, right? We can die, adding our dead organic matter to the earth. And if it just so happens that dead organic matter gets sunk down enough and doesn't flow back up the atmosphere in this fun little cycle here, we can have fossil fuels. Fossil fuels are concentrated amounts of carbon, they're hydrocarbons, right? And I hope this picture does a decent job of illustrating the movement of carbon and the storage of carbon. Well, carbon is a big deal for the greenhouse effect, as said earlier, right? There was a lot of carbon in the earth around us. And this is the key thing when we get into climate change, because the oceans and the land, that may be thousands of carbon here, but this little patch of fossil fuel here is tens of thousands of carbon units, we'll call it, for the sake of this image here. So this little bit of carbon in the atmosphere can cause us issues. This amount of carbon is stored up in the earth. And this carbon right here, the solid earth crushing up a mantle, that's all fossil fuels. as well as those shales and limestones and what have you. So it is a difficult trend because if you have too much carbon floating around, it's thought you get this. All right, let's move on. So I talked a lot about the different locations of carbon. Here's some text to go along with what I was saying. Carbon in the hydrosphere, CO2, of course, can dissolve in water, and you can make carbonates in the seawater, what have you. And that seawater then can be warmed, gases released, right? Density differentials. But a vast majority of that carbon, in fact, is solidified in carbonate rocks as a moderate to long-term storage recipient, holder of that carbon. Thousands of times the carbon that's in the atmosphere is held in the rocks and the carbonates. Fossil fuels, of course, are a good example of this, but interesting fact is the deep carbon that exists, because we are a tectonically active planet, are we not? If the ocean slab, which is super rich in carbon, super rich in carbon, ocean slab, gets subducted, what happens? So that carbon can be released and then float on up. And what happens when a volcano erupts? Lots of carbon dioxide is released. That carbon dioxide comes from, right? Comes from the ocean floor being subducted down. Carbonate-rich sediment can be scraped off to form deposits on the land surface, of course. Carbonate minerals can be, but carbon minerals in general are carried down by subducting plates, where heat releases the carbon dioxide into the magma, mixes in, kaboom! All that carbon's released in the environment again. This is why we say there is massive amounts of carbon in the deep mantle, because this volcano right here is not spitting out this much carbon. It's only spitting out these little blobs. The majority of that carbon minerals are transported into the deeper mantle, where they then could be regurgitated and come back up at some point later on. The positions of the continents, as I alluded to earlier in this video, play a big role in this conversation. Of course, we are aware some 200 million years ago, there's a single continent called Pangaea, more or less near the South Pole. The continental interiors tended to have more severe winters, and for the single large landmass, this all was more severe. You have the organization of the continents plays a big role in the flow, in the movement of the currents of the ocean and the wind. The Gulf Stream exists the way it exists because the United States exists the way it exists, for example. So if you change the puzzle pieces that are the continents of the world around and rearrange them to, say, form Pangaea, you get alterations to the continent and therefore alterations to the carbon cycle. Here's that image I said before of Pangaea. This tectonic activity can come into play when you talk about mountains and climate change. Global cooling, we have determined, followed the formation of the Himalayan mountains when India slammed into the bottom of Asia. Many large subduction-related mountains contain carbonate rock. This carbonate rock erodes and takes CO2 out of the atmosphere. Plus the volcanoes and what have you of the Himalayan mountain range emit ash, sulfur, compounds that cool, and CO2 that warms the climate. A lot of stuff going on here, right? This happened at a very large extent when India smashed into Asia. And a lot of the carbonate rock that consists of the lower mantle, the asthenosphere and what have you, was shot up by that orogenetic event, that orogeny, therefore expelling a lot of the CO2 and what have you. These interactions seem very dramatic, but in fact, as said this last line here, they can do a good job regulating the climate. When ridges spread slowly, oceans deepen and sea levels fall, thereby giving you a larger sink for the oceans and the waterways to hold that carbon. This exposes carbonate rock eventually erodes, taking CO2 out of the atmosphere. And during rapid ridge movement, oceans become shallower, covering up limestone, slowing the weather, decreasing the global albedo. Everything plays an ebb and a flow with itself. And a big part of that is also you can't really do much about it, right? You can't stop the continents from moving. You can't stop the mountains from forming. We don't have that sort of power. Here's an image kind of explaining the process, right? You can consider this the Himalaya. You could consider this not the Himalayas, but this would sort of be the Cascades, what have you, over in like Portland, Washington, not Portland, Oregon, Washington, Canada area. So you have low-level volcanic activity causing the ocean ridges to move, and a low atmospheric amount of CO2 and low sea level, given a high albedo content, creating a unique environment for weathering of limestone and climate change. Contrast that with some high atmospheric CO2 with a high level volcanic activity, slamming these guys together, causing increased amounts of volcanic activity, low albedo due to continents shrinking, and marine limestone weathering away, what have you. Very dynamic, very different environmental impacts. These images may not look very different, but just the amount of water being pushed up here gives you different amounts of ocean to sink the carbon into, because again, let's look at these numbers here, right? Plants, dead organic material, what have you, little teeny numbers of carbon. What's that, 2,000 total? Here we're looking at 40,000, right? And then, of course, increases in volcanic activity, spitting out carbon dioxide, while spitting out ash. It's an ebb and a flow. It's super interesting. It's very complicated, but it's at least important to understand the carbon cycle and these processes and how they work. Again, as I've said in my previous videos, I'll pause here, but I'm not going to. This is not part of like any homework or anything, but if you can answer this question, you probably have a good understanding of what I've been talking about. All right, that was the geology side of things. Let's talk greenhouse effect. You all know the greenhouse effect. I've talked about it before in class. It's a very well understood process, right? Humans release carbon from fossil fuels, CFCs, are the greenhouse gases of the environment. These concentrations of greenhouse gases increase, and it's called the greenhouse effect because the atmosphere acts like a greenhouse. Energy comes in from the sun, tries to leave, but the greenhouse keeps some of the energy back in. That as the greenhouse gases increase in amount, that therefore increases the potency of the greenhouse effect, keeping more of our native energy from leaving the planet and sending it back on Earth, warming the Earth even more. The atmosphere has warmed almost a degree Celsius over the last 50 years. Here's a graph of atmospheric CO2 in parts per million over the past, 60 years here. Straight, almost linear acceleration in that atmospheric CO2. CO2 is a greenhouse gas. We're adding to the greenhouse effect, making a stronger greenhouse, thereby making a higher temperature of our planet. 1-to-1, right? CO2 concentrations over the past, or would that be 140 years? And again, we see a concentrated spike in CO2. This is an artifact of momentum, I guess you could call it. The Industrial Revolution started right back here in the 1800s, and they started pumping out that greenhouse gases. over time, as the greenhouse gases got more and more pumped up there, the greenhouse started building and building and building. And then as it built, it continued to build faster and build faster. And these CO2 concentrations really start to spike up really high. That spike in CO2 concentration, which is again coming from the fossil fuels, the held carbon that we are releasing, makes the temperature rise faster than the temperature had risen fast previously. Again, it has a momentum to it. Consequences of greenhouse warming, again, are obvious. It's called greenhouse for a reason, right? Increased temperatures. What are the results of increased temperatures? That's the important part. Well, one of the results of increased temperatures is decreased plant productivity. In fact, if you've ever gardened before, know anything about plants, you know that plants like things the way they like them. Change temperature a whole lot on a plant, it's not going to be very happy with you. Take an indoor plant, put it outside, massive temperature changes, plant may suffer or the plant may grow exponentially, depending on what the plant wants. But since the vast, basically the entire majority of our diets in some way, shape, or form revolve around plants, right? You may have a steak, but the cow ate grass and wheat and what have you to become that steak. Since the increased temperatures have a usually negative effect on plant productivity, we essentially are killing our food supply by increasing CO2 concentration in the atmosphere and increasing global temperatures. And of course, parasites, other plant ailments can become more prevalent during higher temperatures, which again kills the plants more and more and more. And in a warmer world, we also see increases in things such as precipitation and evaporation. Again, let's go back to the hydrologic cycle. The upfeed of the hydrologic cycle is the water is the H2O evaporating up and hitting the atmosphere, turning into clouds, right? That's how clouds form, is from the water on the surface. If we have a higher temperature, we have an elevated evaporation, we're going to have more clouds that by an elevated precipitation. Clouds are going to rain down more. This is going to produce this upswell, downswell, which is a weather topics, not weathering, weather topics that we talked about in previous chapters, alluding to bigger hurricanes, more devastating tornadoes, blizzards, what have you, because all these things are related to the hydrologic cycle. If you increase the speed and the persistence of the hydrologic cycle, you increase the negative aspects of it a whole lot more, not to mention just more rain, flooding, what have you. The Earth is not very good at quickly adjusting to these temperature changes. Extreme weather events, as said there before, modeling essentially told us things would start to suck more, we'd get more hurricanes, and lo and behold, in 2020, we have, I think, most hurricanes on record already, right? This stuff was predicted in the 80s. Heck, this stuff was predicted in the 50s. Beyond that, you have changes in biodiversity. All aspects of the world are affected, some more so than others. Temperate regions, such as, your Europe and your America regions, a little bit of temperature change isn't going to affect it a whole lot. A bear doesn't really care about a 5-degree temperature change. But in places where it's really hot or really cold, sensitive or specialist species have a problem dealing with this. If the temperature has risen enough that ice packs are melting faster than they usually are, polar bears aren't very good at dealing with that because their hunting ground is decreased. They have a problem finding food. Of course, sea level changes are an issue. This is a big concern in small island nations as well as for coastal communities. Miami, of course, being a prominent example in America. They're having to build walls to keep the rising sea levels out of their condominiums. Effects on people, of course, tropical diseases flare up. These things are all connected to global warming. Not only are we reducing our food income and reducing the land that we can use, but we're also causing there to be disruptions within the ecosystem within the forests and the jungles, what have you, diseases start to flare up and flourish, you can honestly make a not bad connection between the effects that the greenhouse effect is having on the ecosystem and things such as COVID and SARS and swine flu flaring up in intensities that they have. Of course, diseases have always been around, but we're getting a lot of very strong, very powerful diseases back to back to back to back to back. Right? In the past 10 years, we've had 3 diseases that could have been big epidemics, and one of them actually became an epidemic. COVID-19, right? Maybe there's a connection between all this stuff. Oops, there we go. This ties into something I talked about before, the feedback and threshold mechanisms of climate change. Many of Earth's systems exhibit nonlinear responses to climate change. Meaning it's not just a straight effect that happens. Linear means line, right? Many of our systems don't just respond easily to these ebbs and flows. They wobble, wiggle around. Albedo effects, such as melting of ice, causes a loss of white, essentially, and changes vegetation amounts. Albedo, as talked about before, is the energy from the sun shining back up, not being absorbed by the darker dirt that is the Earth. Reduce the amount of albedo you have on the planet, a lot of the sun's radiation sticks with us. These imbalances in temperature and hydrologic cycle can affect plant respiration and photosynthesis. Decay and respiration rates increase when it's warmer, thereby releasing more CO2, which then warms it. Can you see the cyclical nature of this sentence here? Right? It's I say it has momentum because that's a very true statement. If the car's starting to roll down the hill, you need to hit the brakes now, because once the car's going down the hill, you're not going to have a good chance of stopping it. And do you really want to crash, right? Changes in ocean currents that I talked about before. Warmer sea surface temperature slows or stops vertical currents from the bottom heading up. Change in the vertical currents affects the way the oceans move, affects the way that animal life exists within the oceans. If you have sea life that enjoys a certain temperature, they're going to move to find that certain temperature, right? Which can cause fishing to be more difficult. Plankton don't really like, and this tiny marine life that essentially runs the ocean don't really like changes in temperature. And then this affects the degree and the organization of that's what I'm looking for here, the Gulf Stream and what have you, and the ocean currents. There we go. And then, of course, you can talk permafrost, deep sea methane, things like that. If you start releasing permafrost, that holds a lot of carbon, holds a lot of methane. A lot of stuff happens that we don't want to have happen. We can look at here and see a very abrupt changes in temperature due to certain events happening. If a large enough chunk of, say, a glacier drops off and melts, that can cause a very, very drastic effect in the surrounding climate and weather at that event. This very abrupt change here, did it bounce back? Yeah, but the trend continued down. Had it not dropped down, perhaps the trend would have been as severe, giving you a less of a temperature effect, right? It is understanding the climate, understanding not only the natural causes and effects of it, but also the man-made top to it, is, as said by, I'm sure you've heard these phrases, the big issue of our lifetimes and our future lifetimes. It's kind of an annoyance now. 50 years from now, it might be an actual problem. And 50 years from now, it's going to be a lot harder to fix the problem than it is to fix it today. Hopefully, you have an understanding of the process on a macro scale. and on a micro scale at this point. This isn't a climate change class. I can't dig into it too much. However, if you get the opportunity to take some sort of climate change class, not watch a video on it, take a class on it, spend the semester actually learning this stuff in depth, you will only be better for it. And beyond that, right, turn off your light when you go to bed, stuff like that. If you can afford a car that has low emissions, get a car that has low emissions, right? These small climate change effects, these small climate change adaptations can have a large effect if we do it on the correct scale. There are still people that question the validity of this topic, and I question the validity of their information, to be honest. The numbers don't lie. The correlations don't lie. Concentrations of CO2 spike, temperature spikes. The results of temperature change are kind of unquestioned. So I just implore you, take a class in this, educate yourself more if possible. If you have questions on where to find this information, feel free to comment down below. I can provide you a run along the correct way. But taking a class is the most important thing. You're never going to learn as much from a YouTube video as you will from a class. All right, that concludes my presentation for Philander University's Earth Science. This is chapter 21, Climate Change. Again, this is a chapter that really benefits from you knowing the previous chapters. So, coming to the end of this particular book, I hope you've enjoyed it so far. Thanks for watching. Stay safe out there.